Hello and Assalamualaikum everyone. We are from Group 3 are going to present our project-based learning for fluid mechanics course entitled Crystal Ring Water System. I hope you guys enjoy our presentation. So first, let me introduce our presenter for today. We have me, Nadatul Husna, we have Sakinah, and also we have Siti Aisyah. So without further ado, let's go to the first part of this project.
For the abstract, the objective of this project is designing a water delivery system to supply in-house estate which comprises 20 houses. In our project, the water delivery system consists of 6 types of components which are larger water tank, small water tank, water pump, valve, pressure reader and temperature reader. Each unit is connected to each other by replacing PVC pipes. The various types of pipe and pipe connector will affect the major and minor losses. To design a water delivery system, we had to set a dimension of each unit after doing a research and draw by e-drawmax. From this measurement and drawings, we determine the head pump, cost of construction of water delivery system. Through a combination of innovative technology and eco-conscious principles, CRWS aim to revolution resilience water users and reduce environmental impact. For the introduction, the Crystal Ring Water System (CRWS) is suitable water management solution for 20 residential houses, integrating advanced technology and water conservation principles to ensure optimal uses and minimize wastage. This project aims to create a commercial-scale water delivery system for housing estate residents, utilizing both closed and open convection system. This innovative approach promotes a more resilient water supply for the residential communities. A well-designed piping system is a crucial for reliability, efficiency, and safety. It involves selecting appropriate material, considering fluid properties, and sizing to minimize friction losses. Accessibility compliant with industry codes and shock weathering resistance contribute to overall quality. Head losses in the decrease in energy of a fluid as it moves through a piping system, crucial for a system performance and energy efficiency. The Reynolds number characterizes fluid flow, calculated by the multiplying density, velocity, and characteristic length. Material selection is the crucial in energy design, with corrosion-resistant and chemically compatible material. Operating condition, temperature, and pressure also influence material thermal stability and pressure rating. Cost consideration balance initial investment against long-term performance and maintenance. Pumps are integrated in water supply system, converting mechanical energy into the hydraulic energy. The Bernoulli equation and continuity equation help predict flow behavior. The net positive suction head and PSH prevent cavitation and ensure optimal performance, reliability, and longer.
Find several problems before we proceed to this project, which is the first one is the leakage of water. The lack of clean water will be a problem to the residential areas because when there is a leak in the main water pipeline, and these leaking issues should be taken into consideration because as the repair process might be taking some time and costly. Also, the inappropriate pipe material selection can result in leaks because it fails to consider the corrosive properties of the soil in which the pipes are to be installed as well as the quality of water the pipe must carry. When a leak occurs, it will somewhat disrupt the local ecosystem and the water distribution may also differ for each home unit. The second problem that we find is the degradation of quality water. Water degradation is bad problem and it will threaten the residents' health, which are linked to transmission of disease such as cholera and diarrhea. Every month, the residents should check the area around the pipeline and storage tank for any evident signs of corrosion or cracking to stop this from happening. The residents need to avoid spilling hazardous chemicals onto the ground as they could seep into the pipeline and contaminate the water. And the third problem that we find is the excessive cost. Water supply for a housing complex can be achieved at a lesser cost by employing suitable pipe types and efficient routing without sacrificing the functionality. Also, the water distribution system typically consists of valve, storage facilities, fire hydrants, service connection to user facilities, and may be pumping facilities in addition to a network of interconnecting mains or pipes. And last one, these kinds of facilities should be taken into account in order to minimize costs and maintain the entire functionality and purpose of the water delivery system.
For the objective of this project, the primary goal of the project is to develop a water supply system to supply a house estate of 20 houses. The project also to identifies the required element and the type of element to be used in the pipeline system. In addition, the project aims to calculate the efficiency of the system by gathering the relative information such as water flow rate, NPSH and pump efficiency in order to provide the optimal water system for the estate. The project also aims at ensuring the efficiency of the project, particularly during peak hours, and also minimizing the leakage probability for a long period of time. This project also to estimate the electric consumption of the system and also to find the total costs to build the system. These are the some of main components that we decided to build in our pipeline system. The first is big water tank. It's used to store water from the main water pipeline before supply to house estate. Second, small water tank used to store water in each houses that supply from the big water tank. Third, water pump. We decided to put two pumps. First, pumping water from the main water pipeline to the big water tank, and second, to pumping water from the water tank to the 20 houses in the house estate. Fourth is PVC pipe, provides safe transportation of drinking water and water that is used for the household purpose and avoid water poisoning due to leakage during transportation. Fifth is pipe component, is to joining the piping system to make a complete piping system. Sixth is valve, play a role by controlling the water flow rate and regulating the pressure within the system.
This is our schematic design.
Then for the dimension equipment, we only find two dimension equipment. First for the big water tank and small water tank. The big water tank, the volume that we calculated is 44.8 meter cube, while the small water tank, the volume that we calculated is 2 meter cube.
Now we have dimension piping. For the example, first, main water pipeline to the pump A. Pipe diameter we have 0.50, and for the length of pipe we have 13 meter, and for the KL, which is head losses minor, we have slightly rounded entrance, we have value of 0.20, slightly rounded entrance again 0.20, and slightly rounded exit, which is 1.
Before we proceed to the calculation part, these are several formulas that we use to calculate the head loss, to calculate the volumetric flow rate, to calculate the Reynolds number, friction factor, NPSH, and these are the following formulas. In this project, we assume that the temperature of the housing estate is 25 degrees C, which is the average temperature in Malaysia. So, in the water physical properties table, it's not given for 25 degrees C, so we need to interpolate the value to get the density and also the kinematic viscosity at 25 degrees C. The next one, we calculate the volume of the big water tank and also small water tank to get the overall volume of the system. Total volume for overall system, which is V total, is equals to 86.82 meter cubic per day. So, from this value, we can get the average volumetric flow rate, which is Q, in meter cubic per second unit. So, the unit conversion is applied in this calculation to get the volumetric flow rate. The Q that we get is for one house, and we times by 20 because in this project we need to supply to 20 houses. So the Q that we get for 20 houses is 0.02000972 meter cubic per second. In addition, we add some calculation for mass flow rate of water, which is the density times by Q, and mass flow rate is equals to 20.0359 kilogram per second. The most important one that we need to calculate in this project is the head loss. So, head loss is divided by 2, which is major and minor. The formula for major head loss is F, which is friction factor, times L over D times V squared over 2G. And the minor head loss formula is KL times V squared over 2G. In this table, we provide the KL value and also the calculated friction factor and also the steps before we get the friction factor, which is we need to have the Reynolds number. And then I forget to mention that in the material for pipe is the PVC, so the epsilon, which is the roughness we use in this project is PVC pipe material. And then we sum up the HL major and also HL minor to get the HL total for this system.
And for the head pump, we have HP equal to P2 minus P1 over rho G plus V2 squared minus V1 squared over 2G plus Z2 minus Z1 plus HT plus HL total. And for the conditioning, P2 equal to P1 equal to P ATM, which is 0, V1 equal to V2, Z2 minus Z1 equal to 22 meter, and no turbine involved, so HT equal to 0. And for the HP, we got 22.1.014227 meter. And for the table, we have the head pump for pump A until pump 10. For selection of locations, in order to ease the water supplement, we decide to build a water pipeline to supply the water main pipeline to Taman Pematang Badak Jaya Pahang. From the Google Map, the distance between the main water pipeline to Taman Pematang Badak Jaya is 2 miles. The chosen location for the main water pipeline demonstrates carefully consideration of and strategic planning. The situation in an area with a favorable topography, the location minimizes construction challenge and potential environmental impact. Accessibility for maintenance and repair has been prioritized, ensuring efficiency in the long term. The decision also takes into account the surrounding land use, avoiding distribution to existing infrastructure and environmentally sensitive area. Engaging with the local community and obtaining necessary approval underscore and commitment to responsible and community-focused development. Positive suctional heads, which is NPSH. First, we got the formula of P1 equal to rho G plus Z1 plus V1 squared over 2G minus HL minus HT plus HP equals to P2 over rho G plus Z2 plus V2 squared over 2G. And then we set Z2 equal to 0, which is datum. We set V1 equal to 0 because huge tank. And we got the formula of NPSH available, which is P absolute over rho G minus HL plus Z1 minus PV, which is vapor pressure, and over rho G. And for the NPSH for pump A, we get 32.02319 meter. This is calculation for NPSH from pump A till pump 10.
That's for the pump selection. In this project, we have made 3 calculations for pump selection. First for the pump A, second for the pump B, and third for pump 1 until 10. For the pump 1 until 10, we only made 1 calculation since their head pump is similar. In this slide, I show the example for the pump calculation for the pump B. First, I find the Q, which I change the unit for the Q from meter cube per second to gallon per minute. And I also change the unit for head pump from meter to feet. And we use the TACO pump selection to find the head pump, which is 72 feet, NPSH required 7 feet, impeller diameter 171 millimeter, rotational speed 1760 rpm, power input 5.8 HP, and we get the efficiency of the pump 100%. For the pump B, we have chosen the Taco pump with a model of 4009D.
For electrical consumption, firstly, we calculate the total pump power per month, which is we times the total power calculated before by 24 hours and 30 days. So we get 52,682.4 kilowatt. The table below shows the commercial tariff, which is we have tariff category and also current rate. For the first 200 kilowatt, we multiplied by 43.5 cent, and the balance will be multiplied by 50.9 cent, and the total electrical consumption that we get is 26,800 per ringgit per month.
For the construction, we only consider the cost for the piping system, ball valve, big water tank, and small water tank. For the piping system, the total costs that we calculated is 3,283. For the ball valve, 8,964. For the big water tank, 20,024. And for 20 small water tank, 41,300. And for the total costs that we consider is 73,572 ringgit. Next, for the scope. This project we target to supply the water system to the 20 houses at Gambang Pahang. For this project, I made 8 assumptions to find the water consumption. First, the calculation is carried out over the weekend, and each house is occupied by 4 people. There is 2 toilets in each house and no leakage occur. Each house cooks 3 times a day and use the kitchen faucet for 15 minutes each session. Each house has estimated to use the dishwasher once a day. Every person spends 10 minutes taking 2 daily shower. Every individual estimates using the toilet 6 times a day. Every house only uses washing machine once a day. For the calculation, for the total consumption that we assume is 2.36 meter cube. Each houses provided 2 meter cube small water tank, but if there is any shut off from the main water supply, we still have a backup from the big water tank, which has the capacity of 83 meter cube. Next, for the data analysis, from our calculation, we got the total volume of this system is 124 meter cube, and this volume included the volume of big water tank and 20 small water tank. The volume of a big water tank is 84.82 meter cube, while 20 small water tank has a volume of 2 meter cube each. The big water tank has a big volume to ensure there is enough supply of water into 20 houses. Based on volumetric flow rate in our system, which is 0.0200972 meter cube per second, the total heat loss that we calculated was 0.0071 meter. In this system, the total work of water pump is 73.17 kilowatt, and the monthly electrical usage is 26,800. Throughout the system, we made the following assumption, which is first, the water flow inside the pipe is turbulent. Second, the volumetric flow rate Q is the same throughout the system. Third, the effect of sudden expansion is negligible, and fourth, the density of water is constant throughout the system.
Here we are at the pre-selection material part. So we have 5 components that we use in this project. The first one is big water tank. So we decided to have DRP water tanks, also known as fiberglass reinforced plastic. These tanks are crafted by combining glass fibers and hardness with resins. This tank features an interior surface coated with food-grade material, ensuring the safe storage of drinking water, and also their non-cytotoxic layer makes them a top choice for drinking water storage, offering affordability, simplicity in customization, durability, versatility, and an extended lifespan. The second component, which is the small water tank, we select the polyethylene tanks because it serves as a durable and lightweight water storage solution for both residential and commercial purpose, ensuring safe, portable water storage. These tanks are crafted from high-density linear polyethylene and non-toxic material, and also are made of food-grade plastic treated with UV protection. This treatment enhances their strength, make them resistant to UV radiation, temperature fluctuations, chemical exposure, and adverse weather conditions. Despite being made of polyethylene, the tanks lack transparency, making them an excellent choice for minimizing algae formation by blocking sunlight. Next component, which is pipe. We decided to use polyvinyl chloride PVC pipe because it recognized as the most commonly used plastic piping material. These pipes come in various dimensions and sizes, extensively employed in sewer system, irrigation, water service line, railways, fans, and diverse industrial settings. The adaptability of PVC pipes, driven by their safety, durability, cost-effectiveness, environmental friendliness, and recyclability, enables their versatile use from water transportation to the management of industrial of chemical waste. PVC pipes demonstrate versatility for both underground and above ground application within buildings, with additional utility in outdoor settings when equipped with UV inhibitors and stabilizers for protection against ultraviolet radiation, along with a coat of water-based latex paint. And it also function as resistant to common chemicals. The fourth component is ball valve. We choose stainless steel ball valve because it advantages in corrosive media and aggressive environments. They are often used in seawater, swimming pools, osmosis installation with high temperature and many chemicals, so it is suitable to put outside the house. Stainless steel valve usually require a higher operating torque than, for example, brass or PVC valves. This must be taken into account when a stainless steel valve is operated by an electric or pneumatic actuator. The last component that we use in this project is pump. The submersible pump, also called as a well pump, and is fully immersed in water to be extracted. These pumps are used in situations that involve flooding, such as rising groundwater in cellars or basement, flooded pools or flooded areas. Submersible pumps come in different models, and they distinguish themselves mainly in terms of the water that needs to be pumped. For example, clean water submersible pumps, which are used for watering. So, these are all the components that we use in this project. So finally, we are at the last part, which is conclusion. In summary, our involvement in this project has deepened our comprehension of the application fluid mechanics in the water delivery system of a housing estate. This practical experience enabled us to apply the calculations and insights gained from our fluid mechanics course. Before selecting the appropriate pump, we employed various calculation techniques, including well-known concepts such as minor and major head loss, and NPSH, also it enhancing our overall understanding of the subject. From a different perspective, this project taught us to evaluate the system based on its viability, affordability, and also efficiency. These are the three crucial factors in system development. Recognizing that no system is flawless, we now understand the importance of taking safety measures to mitigate potential issues. Similarly, we acknowledge that system efficiency hinges largely on component efficiency. Contrary to the belief that higher costs guarantee better outcomes, we've learned that well-maintained, cost-effective components can yield satisfactory results within their system capabilities. As engineers, our decisions aim for optimal results by relying on knowledge, logic, and facts. This enriching experience empowers us to contribute significantly to the development of improved, more practical, tangible system plans as aspiring engineers. So that's all from us, Group 3, and the next slide will be the references that we use in this project. Thank you.